I would like to introduce Eva Miranda. She's from UPC, CRM and Observatoire de Paris. And let me tell you a little bit about her. She's a full professor in geometry and topology at the Universitat Politécnica de Catalunya in Barcelona. And also she's a member of the CRM and Institute in Barcelona, and also a researcher affiliated at Observatoire de Paris. She's the director of the Laboratory of Geometry and Dynamical Systems at UPC and the group leader there at the research group Geometry of Varieties and Applications. So maybe she was distinguished with an ICREA Academia Prize in 2016 and a Chair d'Excellence de la Fondation Sciences Mathématiques de Paris in 2017. So I guess maybe at a more personal level, we were together at UPC in Barcelona. We met also in a couple of flights, random flights. We got our positions more or less at about the same time. We celebrated together. So actually now it's a pleasure to be here and presenting her. So now going to mathematics. She's going to tell us about looking at Euler flows through a contact mirror, universality, and Turing completeness. Thank you.
Thank you very much, Mar, for this nice introduction. I'm also very glad that you are introducing me, because you are one of these who wanted to be has always been between two different lands. And I identify myself also my research between two different lands. So it's a pleasure for me that you are introducing. Can everyone see the slides?
I guess it should be fine. We are seeing them.
Okay, good. So I hope I don't forget anyone. I wanted to essentially first thank the scientific committee for proposing me to speak here at the European Congress of Mathematics. For me, this is a honor. This is my first time in such an important workshop, big meeting, and I'm really thankful for this opportunity. So today I'm going to talk about, well, I gave this long title, right? Looking at the Euler flows through the contact mirror, universality, and Turing completeness. There are many words here, but let me highlight Euler flows, contact mirror, universality, and Turing. And these are 4 key words for my talk. Today, I will not explain, I have been for a long time working in Poisson geometry. We had a very nice talk yesterday by Marius Kranik on Poisson geometry. So indeed, I decided to twist a little bit and talk about an adventure I had in research the last 2 years, which is really relating 2 different fields, which is that of Euler flows and that of contact geometry. And well, in this picture here, we have some flows with all their complexity, right? And who can tell us that such a complexity can be indeed connected to the simplicity that the word geometry implies? This picture here, which I borrowed from the webpage of Patrick Patrick, it's a picture of a contact structure on S3, the standard contact structure on S3 that is associated to the hot vibration that all of you are familiar with. So today I'll try to connect these 2 worlds, which are apparently different, and I'll try to give some applications of this connection. Let me see. Oh, it seems I have a problem here. I'm going to, 1 second. I have a technical problem. I have a technical problem. I'm going to share again. I'm sorry for this.
No problem.
I don't know, when I stop sharing, I don't know, when I share and unshare and I leave full screen, sometimes there are problems. I'm sorry. I apologize. Okay.
Does it work? Okay.
Now it works. So before I forget, and this is very important, I'm here talking about joint work with other people who have been fundamental in this work. This work wouldn't exist if any of these people here wouldn't be in the team. And I want to highlight here Robert Cardona, who was my former PhD student and who has been a gear and a main character in this adventure. He is now probably one of the world experts in Turing completeness and its relation to topology. And here, Daniel Peralta-Salas, an expert in fluid dynamics, and Fran Presas, an expert in contact geometry. So what I'm going to explain to you is what happens when you put people from different fields in the same room and you ask them to collaborate. So out of our collaboration, we have here several papers. I want to give a flavor of these papers. Maybe I will not have time to explain all the details, but I want to give a flavor of these papers, which is one old paper, well, old by now, in 2019. We wrote a paper on universality of Euler flows, which is still on the archive, not published. And then a paper where in this paper of universality of Euler flows, we were giving some construction in high dimension. And then we managed to make this construction work in dimension 3. And this was published in the PNAS very recently. And just in April with Daniel and Robert, we also went a bit further and studied the Turing universality of the Euler flows. And what happens with these two papers is that here the Euler, the universality and everything is connected to a class of Euler flows, which are Beltrami fields, which are characterized by being stationary. And in the last work, we have a time dependence. And the last work builds on, very importantly, in a very recent work by Francisco Torres de Lizaur, who I also want to thank here. So this is the timesheet of our adventure. If I have to put some years and main facts that introduced us to this topic, I will start with a paper by Chris Moore, where he was asking if hydrodynamics is capable of performing computations. And, you know, another random fact is that 29,000 rubber ducks were lost in the ocean. These rubber ducks were rubber ducks like this, where you can find, or maybe more like this. I have a collection of them in my home, but I don't have the 29,000. Why? Because they were never found completely. And the question is why they were never found completely. How can be this related to the question of Moore? Well, these rubber ducks were some ducks sent from China to Tacoma in the States, and there was a big storm, and you know the cargo was lost. And then what happens with the rubber ducks? These rubber ducks started to appear everywhere on the world, around the world. And indeed, in July 2007, one rubber duck even showed up in Scotland, right? And still, these rubber ducks have not been totally recovered. And now I'm going to talk about tau, okay? What can be the connection between a rubber duck, tau, and Chris Moore? Well, this talk. In 2017, Terry Tao asked about universality of Euler flows. He came to this question, which I will explain what it means universality in a minute, be patient. But the motivation for him came from an old paper, well, not so old, 2014, where he produced blow up for averaged Navier-Stokes equation. And then he has been trying to apply similar ideas, which build up on some dyadic models that were used in this averaged Navier-Stokes to find blow up for Navier-Stokes. Of course, this has not been achieved, otherwise we would know by now. And in his mind, well, as you can think as the Euler flows as a reduced or simplified model where the viscosity is 0. And then, I mean, he even has some heuristic argument that makes you feel that if you can solve this for the Euler equation, then maybe you get some good information for Navier-Stokes. And well, among his discoveries, one conclusion that he reached is that, well, the metric to use Euler equations with the standard metric is not good enough to find such counterexamples. That's the first conclusion of his several works dating back in 2014. And another important conclusion is that you need to, that dimension 3 is maybe not the right scenario. So maybe you need to increase the dimension of your manifold. Maybe you need to think of the metric as an additional free random, as an additional variable that allows you more flexibility in the solution of this problem. So with this idea in mind, in November 2019, we proved indeed that Euler flows are universal, and not, so this means that any dynamical system, think of any dynamical system, you can represent it by changing the metric and increasing the dimension of your manifold as an Euler flow. But this Euler flow is a stationary. So let's say from a point of view of PDEs, it's not so interesting. Let me spot this at this precise moment. But for us, this was already interesting from a dynamical point of view, because you have a way to put, you have a box to put all your dynamical systems. So from that point of view, it's like an interesting experience. I must confess that how did we came to that question? Indeed, we had been working with Robert and Daniel on a different problem. We were working on fluid dynamics on manifolds with boundary, and trying to apply B-symplectic geometry, which is something I had been working on, to that problem. And then we finished the paper, and coming back in the train, I was in the AVE, I was a bit bored. And then I was looking at the Twitter, and I found that somebody was tweeting about a post in the blog of Terry Tao, where this question was asked. In that paper with Robert and Daniel, we were using the strength of contact geometry to solve a problem in fluid dynamics. And then I thought, let's try to play this same game. And this is how our adventure started. The adventure went on when in December 2020, we gave this construction in dimension 3. And then we found a construction which is time dependent, of course, in higher dimensions, fitting also the program of Tau. This is a paper that with Robert and Daniel, and it's on the archive at this moment. Okay, let's introduce some definitions. Let's talk about classical Euler equations on dimension 3. These are the classical Euler equations on dimension 3, okay? Where here we use what we explain to our students in vector calculus, okay? And then if you think about the mnemonics of these equations, okay, you can indeed think of these equations also on Riemannian manifolds. From the perspective of Tau, this makes a lot of sense, and many other people have already been working on Euler equations on manifolds with arbitrary metric. So here I want to defend that it's good sometimes to put arbitrary metric on Euler equations. And then you can write these equations, okay? This first equation, you can write it using the connection associated to your metric, okay? And the second equation, which is the divergence, it's the same, because you can indeed define the divergence using the volume form and the metric associated to your structure, okay? And of course, this is a PDE, and the unknowns are the velocity field and the inner pressure, okay? So here today, I will mainly concentrate on a class of solutions, which are called steady or stationary Euler flows, which model the fluid flow in equilibrium. So from a point of PDEs, maybe this is just small example, okay? But what's nice about them is that, okay, you can encode any dynamical system in that. This is quite beautiful. And then these equations, because you don't have dependence in time, can be written this way, okay? And now I'm going to start playing my game of crossing the mirror. By the way, I didn't say that this first picture here of crossing the mirror this is Alice looking through the mirror, okay, looking through the looking glass. I don't know how it's called, this book, but on one side Alice is working on fluids, and on the other side Alice is working on contact structures. Okay, so now I want to say looking through the Alice through the looking glass. I think that's the title. Okay, so now I want to let Alice go through the looking glass here, the mirror. Okay, and a way to do this is that, well, vector fields, geometers are happy with them, but if we have a metric, right, we are tempted to use it somehow. One thing you can do with this metric and with the volume form is to dualize such equations. Then instead of having some equations in vector calculus, you have some equations with forms. As a geometer, you maybe feel much more comfortable. They are the same equations. You can choose. If you prefer equations with vector calculus, then you take the first line. If you like equations with form, you take the second line. Okay, these are equations of the stationary Euler flows, okay, when you don't have such dependence. And what's nice about them is that they have a geometrical flavor. We can already see this because we have forms associated to them. But we're going to see that these forms have a geometrical meaning in a second. Well, let me highlight that what is a Beltrami field? A Beltrami field is a field whose curl is proportional to the vector field, and the curl can be also defined using this metric, okay? And the divergence is zero. That's the definition of Beltrami field. And indeed, Beltrami fields are stationary solutions. Example of Beltrami fields are that we know from different sources are Hopf fields on S3, if we are familiar with geometry, okay, which are the one here, these two vector fields, and the ABC flows on the three torus. Okay, now I need to introduce some geometry. And I'm going to do it with this scheme. Okay, if you don't know anything about symplectic geometry, the only thing you need to know is that there are plenty of geometries controlled by forms. There was a mini symposium in this Congress, but I'm going to highlight two of them: symplectic geometry and contact geometry. Here on the left, you have symplectic geometry that it's in red, that fits even dimensional manifold. Okay, and then the geometry is governed by a two-form, which is non-degenerate and closed. And this allows you to write, for instance, Hamilton's equations, okay, in a language of forms. You may or you may not like to do such a thing, but you can do it. And then the equations, Hamilton's equations, can be just, you have the total energy of your system, okay? This is a function, the differential of a function is a form, and then you can just solve by duality, and you get a vector field with respect to this two form. You get one vector field if you solve such an equation, which is the contraction of a vector field with a two form, okay? And this vector field has a flow whose flow is precisely the solutions of this vector field. If here I take a particular type of symplectic structure, which is Darboux form, which locally all of them are the same, by the way, so it's not such a particular case, but it's general, then indeed the flow of such a vector field, the equations of the flow are Hamilton's equations, okay? So symplectic geometry was born indeed to give some geometrical context to the movement to many problems in physics. Okay, what about this? Its odd-dimensional counterpart would be contact geometry, where the dimension is odd, okay? And then the geometry is governed by a one form. And this one form satisfies some condition of such a, you can think of this, like this is a top form on your manifold, and you assume that this defines a volume form, and you can think of this as a non-integrability condition for the kernel of alpha. If you look at the kernel of alpha, then the picture here, which I also borrowed from the webpage of Patrick Masson, represents indeed this non-integrability condition for the standard contact structure on R3. And there, of course, you have a way to define Hamiltonian vector fields, but what's more important from a dynamical point of view are red vector fields, which satisfy two conditions. The first one is that the contraction with the differential of alpha is zero. So this is in the kernel of this distribution, if you want, and alpha with the red vector field equals 1. So indeed, you make a choice in this. In the picture that I showed in my first slide of the Hopf vibration, this would be precisely the Hopf field on S3. Okay, so this is my 1-minute summary of geometry. And then one important aspect of the stationary Euler equations, which we can write like this as one forms, remember, is that this one form here is a contact structure. That's an easy exercise that I comment here. You can really prove it very simple, and the solution is here. And indeed, this is one of the implications of establishing this contact mirror. And this is a theorem by Edner and Grist, which was formally observed some time ago also by Sullivan, but completely proved by Edner and Grist in a beautiful paper, where they give a one-to-one correspondence between rotational non-singular Beltrami vector fields, which mean vector fields that never vanish, and for which this function is non-vanishing, and red vector fields, which you need maybe to reparameterize. So I leave the solution of this exercise here. What we did with Roberta and Daniel, indeed, first is to extend this equivalence to this model of manifolds with boundary, where you have these big contact structures. And then also with Fran, we proved that such a correspondence holds in any dimension. So what you have is a magic mirror, okay? You have a magic mirror. On one side of the mirror, you have fluid dynamics, you have Beltrami fields. On the other side of the mirror, what you have, indeed, is contact geometry. So what you can do is, I have a problem in fluid dynamics, okay? I cross the mirror, I solve it in contact geometry, and I need to cross the mirror again. Today, I'm going to present two applications of this of this mirror, which is a first one, it's an application to prove the universality of Euler flows. And the second one is the construction of this universal three-dimensional Turing machine. But there are others. For instance, the initial application of the Weinstein conjecture, and then a very nice recent work that we did with another student, Cedric Ohms, and also Daniel Peralta-Salas, relating indeed singular periodic orbits with escape orbits in celestial mechanics. And for that, we used indeed, we reversed the mirror. So we solved the problem on the fluid part and applied some result, beautiful result by Karen Uhlenbeck. Today, I will just focus on these two aspects. Whenever I use this mirror, I'll put this picture. Okay, let's go back to the problem of Tau of universality of Euler flows. His question was, he asked this question in February 2019, can any incompressible vector field be embedded as an Euler flow by increasing the dimension of the manifold? And his question, as I said, was connected to his program to find the blow up of Navier-Stokes equations. And indeed, his motivation is to create indeed an initial datum that is that you plug in Navier-Stokes equation, and that is programmed to evolve to a scaled version of itself, like a von Neumann self-replicating machine, in such a way that you are indeed clustering a lot of energy, and then you have this explosion. Indeed, this is totally heuristics. There's not proof of this yet, otherwise you would know. But this is his idea. So indeed, in his paper in 2014, where he solved the problem, or 2016, I think it's 2014, where he solved the problem for the average Navier-Stokes equation, he was following some dyadic models that you could think of some kind of discrete models. And with this idea in mind, this is how we connected this to the Turing completeness. Okay, and how can I explain universality with two images, with three images? I can explain it like this. Well, here I have a random picture of Barcelona in December. Call me picky. Yes, I chose a nice picture of Barcelona. Why not? It's where I live. And this is also a nice picture of Paris, though it's not clear that you can find Santa Claus skating always. It's not very French, okay? But well, you can spot some difference. Never mind, if you are far away, you will see no difference. So if you go to the international station, maybe you don't see so much difference between the two. So that's the idea. You have a dynamical system, and if you go far, far away, then maybe you don't see such difference. So indeed, when the Euler flow, so exactly we started with a particular case of a stationary flow. And why? Because you have this mirror only in the stationary case, okay? So when the Euler vector field is Beltrami, we can use our magic mirror. So then the question, exactly the same question that he was asking, we are asking now in our geometrical language. And the question is, can we realize a vector field on a manifold as a red vector field on a bigger compact contact manifold? Of course, if I don't allow myself to increase the dimension of the manifold or to embed this, the answer is no. It's very easy to find counterexamples. Okay. So, well, indeed, we asked this question initially to Fran, thinking he would know the answer because he has all his life working in contact geometry. So at the beginning, he said, oh, this is, I don't know. Oh, this is an interesting question. So we started to work on this. A necessary condition for this to happen is that the vector field, well, question is, do you need some conditions? Of course, this took us a while. And the condition, what we found necessary, is that the vector field is geodesimal. The condition of geodesimal vector field, for the ones in Riemannian geometry, they know that this is a vector field for which okay, where you have, of course, a Riemannian metric, and for which the orbits are all geodesics of unique length. There is a way to encode this definition with forms, and then you need to have a one form such that alpha of x equal 1, and the contraction with the differential of alpha equals 0. Look, this looks like the red condition. What's the difference? That you don't know that alpha satisfies the non-integrability condition. So, so if you have such an alpha, can you deform such that it satisfies the non-integrability condition? Is this condition sufficient? This recalled us of the H principle. Indeed, inspiration came from this beautiful paper of Borman, Eliasberg, and Murphy, where they prove that any almost contact manifold or any almost compact manifold is contact. Indeed, this comes like this has a long story, but to make it short, in 3 dimensions, this condition of being almost contact can be thought as what is called a formal condition, also in algebraic topology and in the story of H principle. Okay, and then you need to have some abstraction conditions, some abstraction theory in algebraic geometry vanishing. Okay, and these conditions automatically vanish in dimension 3. So indeed, all 3-dimensional manifolds are contact. This is great news. And what happens with higher dimension? Well, you have such a condition. Indeed, and in their proof, okay, they were using an H principle of such a result. Okay, so indeed, this is what also is related to this concept of flexibility, that you can really deform. And this is the idea what we have. We have this red vector field, you know, well, you have this, this geodesical vector field, and you want to deform it to a red vector field. Okay, so you have those equations, but you need in a way to deform this alpha. How can you do such a thing? Well, you do it with the H principle. If you are not familiar with the H principle, this is a 3-steps process. It's everything in life. Everything in life can be done in 3 steps. First one, you have a goal. You want to solve an equation. Second one, you cannot solve the big equation, so you say you have a semi-goal. And maybe you can solve the linearized equation, okay? Or the formal equation. And then the third step of the solution of any problem requires a miracle or an inspiration, which in the case of the H principle, this has been used in PDEs, etc., for a long time, and in geometry. You need to prove that there exists an homotopy that allows to deform a formal solution to a honest solution. And you need to be lucky for that. Okay, you need to have, you need that the system is what is called to have high codimension, to have this kind of vanishing of all these formal algebraic conditions. That's the idea. Okay. Well, I have already said this, but let me introduce some language because I'm going to use Eulerizable. What does it mean Eulerizable? I have a vector field and I say it's Eulerizable if on the same manifold you have a Riemannian metric, okay, compatible with the volume form, such that this vector field satisfies the stationary Euler equations, okay? And the condition of Euler extendable, the difference between Eulerizable and Euler extendable is that in Euler extendable, I need to extend to higher dimensions. Here I put, just for simplicity, the time periodic case. If it's not time periodic, you can do this, but then you don't have a compact, you cannot guarantee that you have a compact ambient space, okay? So if you have a non-autonomous time periodic vector field, okay, you say it's Euler extendable if you have an embedding of the product of your initial manifold with S1 on a bigger manifold, which is compact of dimension n, and you can assume it's a sphere, or you can take your favorite compact manifold, okay? For which, well, indeed, what we are using is that it has a contact structure, so you better take, I mean, in our proof, we need it to be contact, okay? Because in our, of course, we are going to use this correspondence, okay? Well, you'll see. And so our definition is that the push forward of the original vector field plus this periodic dynamics is precisely a vector field which is an Eulerizable flow on the sphere. Okay. So what we proved indeed is that Euler flows are universal. This means that they satisfy the condition that any non-autonomous dynamics is Euler extendable. Also, if it's non-time periodic, then you cannot guarantee that it's compact. Then, okay, we prove that the Euler flows are universal. And what is the dimension of the ambient manifold? The ambient manifold is the sphere, or Rn, and the dimension is the smallest odd integer between these two. 3 dimension of n plus 5, 3 dimension of n plus 6. If you are here to listen about the 3-dimensional case, then you think, this is not useful for me. We are going too far. Wait a minute. Okay, can you say something about the metric? It would be wonderful if you can guarantee that the metric is Euclidean. But Tao already said it. It's going to be strange that the metric you can keep the metric Euclidean. In our case, we can guarantee that the metric is Euclidean outside a ball, which contains the image by the embedding of your initial manifolds times 1 in the time periodic case, or time r in the Rn case. How do you prove this? Well, of course, we are going to use the contact mirror. Then the question of universality, you can say it in a different way, but studying the universality of high-dimensional red flows. Okay, sorry. The red flows are geodesical. This I already observed, because the equations are the same. So if you pull back, you have those equations, okay? But the converse is the hard thing, is to prove that any geodesical flow is rep extendable. And this is what we did with the help of the H principle. So we prove that if you have a compact manifold and a geodesical vector field, you have this condition that I will drop in a minute, okay? Because this condition you may not like. Oh, geodesical vector fields, I don't like that. Okay, don't worry. Then there exists a smooth embedding that puts this in a higher dimensional sphere of dimension 3, dimension of n plus 2. If your vector field is already geodesical, you have a better bound. Okay, that's the conclusion. And you have a one form defining the standard contact structure such that this embedding is an invariant submanifold of the red vector field, and such that you are pushing forward the dynamics into this red vector field. So it's a very sophisticated way of saying that if you increase the dimension, you can solve the problem. And if your initial data is geodesical, then the ambient manifold is dimension 3 times your initial dimension plus 2. Okay, how do you do this? Well, first, a little bit of linear algebra, which I will not disclose here. You can embed your initial pair, your manifold and your geodesical vector field on an open contact manifold of dimension 2n minus 1. You can think, for instance, that you are working on the spherical cotangent bundle, which has a nice contact structure. And then you want to embed such an open set on a compact manifold, okay? Here you use a result by Gromov to embed it on a sphere of dimension 4, dimension of n minus 1. I am a geometer, so I'm not so picky about dimensions, but I know people are picky about dimensions. So what was taking us most of the time was to reduce this dimension, okay? To sharpen this dimension, which we could do with the help of an H principle. So this theorem of rep embeddings, indeed, what it's doing is to reduce this bound, okay? And it reduces to a 3 dimension of n plus 2 if you don't know anything about the contact structure on your target. And if the contact structure of your target, if you have an embedding is over twisted, then you can do it a little bit better. And here is where indeed you use this result of Borman, Eliasberg, and Murphy. Okay, final step. I'm sorry because I'm a bit late. The final step is how bad is the geodesical condition? I said, don't panic. If you don't like geodesical vector fields, I'm going to give you one for you. If you take a time periodic vector field on a manifold, what happens is that the suspension is geodesical. You take the product with S1, you take your initial vector field, and then you push forward to the suspension, so you have this new vector field. And what happens is that for the push forward on the suspension, this means increasing the dimension by 1, okay? Then the one form differential of alpha is a one form that satisfies the conditions of geodesibility. So what I'm saying is that geodesibility is not a big deal. By increasing the dimension of your manifold, you can always meet such a condition. So there we go. Now we need to take the former bound and we need to put this plus 1 in the 3 dimension of n plus 1. Okay, so you need to plug here dimension of n+1 if your initial vector field is not geodesical. Then by the previous theorem, what you get is an embedding extending the initial vector field on these dimensions. Of course, of these dimensions, one is going to be odd, and this is the one you need to take because you need to have this contact structure. Now, time to use the mirror. You have solved your problem on one side of the mirror. Time to cross the mirror again. By the contact-Beltrami correspondence, you know that there is a metric and a volume making this vector field into steady solution of the Euler equations. And that's how you solve your theorem. Well, I was very happy about this result. Indeed, I was super happy, but then, well, you give some talks. You give a talk in an analysis seminar and people tell you, I'm interested in dimension 3. I'm interested in Euclidean metric. Can we do something for you? Yes. But before I explain this, I'm going to explain an application to prove Turing completeness. Now I'm very late in my talk, but I have like a formal definition, but we have to live with this definition, okay? Because we don't have much time. And the definition of Turing completeness, okay, of Turing completeness applied to Euler flows is that a vector field is Turing complete if it can simulate any Turing machine. In other words, if the holding of a Turing machine with a given input is equivalent to certain bounded trajectory of the field entering an open set of them. This is a hands-waving definition, but I have a precise definition, but I think I don't have time. Maybe in the questions I can show it. So, well, this is a picture of the situation. Okay, you have a way to associate to your Turing machine points of the flow, and when this flow enters a certain equation, okay, in the world of Turing machines, the most important thing is when the machine stops, is the hold. When it stops, it's exactly the hold. So the holding of this Turing machine is equivalent to this flow entering an open set. Then we have, with this already hand-waving definition of Turing complete flow, we can find an application. We could find an application of this contact mirror, because indeed you can do when you can give the definition associated to flows, to diffeomorphism, etc. It's a definition concerning systems of maps. You can talk about Turing complete maps. And indeed, Terry Tao proved that on T4, you have a diffeomorphism encoding a universal Turing machine. So what you do is to promote this diffeomorphism, okay, using this idea of suspension, and then using the former theorem, you can indeed embed this Turing complete machine of Terry Tao, okay, into a sphere, into an Euler flow on a sphere of dimension 17. This dimension 17, I let you count it, is applying the former result to this T4, and you need to promote it previously, because you don't know if it's satisfied. If this is going to be a return map of a geodesical vector field, you need to promote it with the suspension. And why is this Turing complete? Because you start with something which is Turing complete, you do a suspension. This is something that you can compute, and then you apply the H principle. And the H principle, we know it's given by holonomic approximation, so it's algorithmic. So that's a nice application, but again, you make a talk in a seminar of analysis where it's 3 dimensions. Let's go there. Can we do it better? In the last minutes of my talk, I will explain very, very briefly 2 ideas how to do this in dimension 3. So what we proved with Robert, Daniel, and Fran is that there exists an Eulerizable flow. Sorry, this is Peralta-Salas, an Eulerizable flow on S3 that is Turing complete. And the metric that makes this vector field a stationary solution of the Euler equations can be assumed to be the round metric, or the Euclidean metric, the standard metric, in a complement of an embedded solid torus. Okay, now I'm going to think of Alan Turing. Alan Turing, in 1936, he proved that the halting problem is an undecidable problem. Everyone was very excited because this was one of the first problems to be proved to be undecidable. So we just apply, because our definition of Turing complete implies the halting problem, because we have a flow, okay, and we say that it's Turing complete, okay. Remember, this hands wavy definition is enough if given an input of your Turing machine, this is equivalent to the flow, the trajectory of your vector field entering a certain open set. So as a nice corollary, there exist undecidable fluid particle paths. So there is no algorithm to decide whether a trajectory will enter or not an open set. This would explain why these 29,000 rubber ducks that were lost in the ocean were never found back. Okay, you can be picky. The metric is not Euclidean, but it's a nice metaphor. So if you want to send a message, a love message, don't use a button, okay? You use a WhatsApp. And what about Tau's program? It would be nice if this Turing machine would give us the blow up. It doesn't, okay? It's too simple because it's a stationary solution. And well, here I put the Navier-Stokes equation with the viscosity, blah, blah. The important thing, that's the solution when you plug it. So, okay, what happens is that here you have the viscosity of Navier-Stokes equation, and the exponential decay implies that it can just simulate a finite number of steps of a Turing machine. So it's not good enough. And in the last 2 minutes, well, here I have a definition of formal Turing machine, but what I'm going to give for you is 2 images of Turing machine. I'm not giving a formal definition. And the one is the one of the tape, okay? And the second one is the one of Conwan's Game of Life, which is a boring game. You don't have any player, but you have a system that evolves and you have some rules. This is indeed what is called a cellular automaton in computer science. And von Neumann proved that every Turing machine has a cellular automaton which simulates it. So indeed, this is a black box of my talk, how we were able to produce and to construct. And in the last 2 minutes, because we started a bit late, Mar, I'm going to take 2 minutes to finish. It's okay?
Yes, it's fine. Yeah, okay. We started late.
Okay, thank you. So indeed, what we did, and that's a beautiful construction that I really wanted to explain, but it's too short. This is going to be a black box. What we did is to use some construction of Moore. Indeed, Moore proved that a Turing machine is equivalent to what is called a generalized shift, which you can think of a generalization of shift in dynamics. Indeed, and this puts dynamical systems and it puts shifts on the same page. Okay, so one thing we did was to fill in some gaps. So he was giving some construction using the Cantor set. Okay, and the Cantor set so the square Cantor set. You take the product, you know the Cantor set. You just take out the middle, of the intervals, okay, and you can associate indeed an expansion of your any point on the Cantor set associated to a Turing machine in a very beautiful way that I wanted to describe, but no time. And then the nice thing is that he was constructing the generalized shift. Okay, what we want to do is we want to construct on the sphere, we want to use this generalized shift. This generalized shift for him, it was on a square Cantor set. What we did is to extend from the square Cantor set to a disk on R2, standard disk on R2. Okay, then we have to go to S3. How do we do it? Well, first thing is that we extend this to an area preserving diffeomorphism. You know why we impose the condition of area preserving? Because we want this vector, we want this mapping indeed to be the time one map of a red vector field, because we want to use our mirror. Okay, and therefore, because I didn't say it, but it's a consequence, the red vector field has to preserve the volume. Therefore, we need this to preserve the area. Okay, and then what we did is to promote the construction of Moore to a diffeomorphism of the disk, which is the identity. We needed to be the identity in the neighborhood of the disk, and which restricts to this construction of Moore. Okay, and that's I must say a beautiful construction that indeed Robert Robert was at the end of the thesis and he just nailed it down, I have to say it. So and one nice thing is that now you can promote, here you have your Turing machine, you are extending your Turing machine to a diffeomorphism of the disk, and now you can take the suspension of this. So you can think that this diffeomorphism is the time one map of a red vector field. That's what we proved, okay? So we proved that if you give me any contact three manifold, we know that any three manifold is contact, and you have an area preserving diffeomorphism of the disk, which is the identity in a neighborhood of the boundary, there exists a defining contact form whose associated red vector field exhibits a Poincare section whose return map is conjugated to your initial field. This is the same as saying that the time T map of your red vector field is such a mapping, okay? So you do this construction, time to look ourselves in the mirror. We are doing contact geometry. This was done using contact geometry, very basic contact geometry in dimension 3, I must say. No H principle here, just hands-on. Moser theorem, the idea of the formation, hands, you put your hands and you do it. It's great theorem, and you deform your contact structure. Then, well, what happens as a consequence of this is that, okay, this constrains your contact form, your contact structure on this toroidal domain, which is the product of the disk with S1. You can think that you have such as a suspension. And then, but outside this, on the sphere, you can assume you have the standard contact structure. Now you cross the mirror again. And when you cross the mirror again, you associated to this red vector field, what you have is a Beltrami vector field on a three sphere. Okay, which is Turing complete. So this proves your theorem. Can you do this even better? Can you represent any dynamics on by a Turing complete time-dependent Euler flow? Yes. Okay, but this is a consequence of, as I said, and a big merit of such a result is a result of Paco, Francisco Torres de Lizaur, who proved indeed that you can embed any polynomial vector field. Well, he gave a more general result, but here what we use is that if you have a polynomial vector field, you can embed it on a compact manifold. You can look at it by increasing the dimension as an Euler flow. So what we did indeed is to find a Turing complete polynomial vector field. Indeed, it was not on a sphere. We found it on a paper in computer science by Grasa, Campagnolo, and Buescu. I shouldn't forget Jorge Buescu. And such a result was done on, this was on a plane, on R2, okay? So what we did is to promote this to a sphere, okay? Well, you can do this sphere in any dimension, from Rn, this was on Rn, and you can promote it to a sphere of any dimension, just by indeed thinking of the stereographic projection and a bit trick of reparametrizing the time, so that you skip problems in the North Pole. I'm going to point to the difficult part of the proof. So what we prove is that there exists a smooth compact Riemannian manifold such that the Euler equations are Turing complete. In particular, the problem whether the solution of an Euler equation with initial datum will reach an open set. I must say here that the definition, the neighborhood, I didn't say it, I didn't stress it. When you have this time dependence, the initial condition, when you move it, you think now you take a neighborhood of an infinite dimensional manifold, as Tao was doing in his former papers, which is the set of vector fields which satisfies the condition that the divergence is 0. Okay, so you need to consider this set here, divergence-free vector fields. Okay, and then a neighborhood is a neighborhood in this infinite dimensional set. So the definition is the definition of Turing complete. The formal definition is this one. Okay. And so in particular, you get a condition of undecidability just by applying the indecidability of the halting problem of Alan Turing. And well, what about the manifold? Now, before any analyst here asks me, I'm going to myself declare that the manifold has a dimension of order 10 to the 35. And you can think of this manifold as a product of SON times a torus. And this comes a little bit from the method of proof, okay, of Paco, of Francisco Torres de Lizaur, where you have some spherical harmonics in his proof, and that's what inspires such a product. Also in certain papers of Tao, you have similar constructions. Okay, so this is the last result we obtained. And what's next? Well, what's next? And with this, I finished. Sorry, I'm over time. What's next is, okay, you may ask, can you do it better? I mean, can you provide an example of a construction in dimension 3 which is Euclidean? This is not, of course, in the papers I mentioned, but this is a work in progress that we are doing with Robert Cardona and Daniel Peralta-Salas, and I can tell you that the answer is yes, but there is always a price to pay. You lose compactness, okay? Another question is, can you relate the computational complexity? This is what you are proving with this Turing completeness. You have a computational complexity with a topological complexity. Is there, for instance, can be the entropy zero? That's a natural question. Can you find Turing complete with entropy zero? Yes, but you need to do very strange things. This is some other thing. Can you relate this to polygonal billiards, in which case you won't have this, you will have positive entropy? Yes, all this is also work in progress, and something that we have already proved, and this is already written down, it's still not on the archive. This will be part of my proceedings to the ACM with Robert Cardona and Peralta-Salas. We can prove, related a little bit to the Weinstein conjecture of existence of periodic orbits, we can prove that it's undecidable to know if you will have a certain periodic orbit starting at a certain point. This is interesting, especially if you cannot prove the Weinstein conjecture. If you cannot prove the Weinstein conjecture and you can prove that it's undecidable, let's say this is a first step towards understanding what's going on with the Weinstein conjecture in higher dimension or in other situations, for instance, if you have singularities. And with this, I thank you and I finish my talk. Time for questions. Thank you.
Okay, thank you, Eva. We have already one question in the chat. So I'll read it. Will any part of the method work for Euler equation on a domain, say with non-slip boundary conditions?
With non-slip boundary conditions, what do you mean?
So I mean, for the Euler equation on the whole space, but on a bounded domain with right boundary conditions.
Yeah, you can make this work because the construction, okay, I was too fast and I already apologize. At certain point of the construction, we were embedding things on an open set. And then this open set, you can always embed it on a compact manifold thanks to Gromov. So you have a way to compactify your problem from a domain, from an open domain. So the answer is yes.